Hey guys, welcome back. This is Mr. Saleh. Today we're talking about Unit 1 for AP Chemistry. We're going to talk about atomic structure. Okay, so with atomic structure, we're going to talk about a few different things. Look at our vocabulary. We'll talk about significant figures, excitation, relaxation, and the electromagnetic spectrum, photoelectron spectrum, Coulomb's law, electron shielding, effective nuclear charge, and quantum numbers. Okay, so a lot of what we're talking about, this whole section, is going to look at electrons. Significant figures is going to be a separate little bit there. Okay, so starting with significant figures. Significant figures are the meaningful digits in a number that is reported from an experiment or from lab based on precision, right? So if we look at this example here, if I have one apple and I have two different balances, the first time I get 130 grams on my first balance. My second balance, I get 129.592, right? If I look at that number, 129.592, that can get rounded to 130, right? Which is the same as our first number. It's the same thing. So our number is not changing. What's changing is our precision. We have decimal points here. That means we are more sure about our number than we are with that 130. Right, so if we look at these balances down here on the pictures, this first one reads 0.00, the second one is 0.0000. We have two extra zeros there. That means the balance on the right is more precise in its reading. It's going to give us a better number, a number that we can rely on more. Right, so anytime in science we're doing a lab or we're doing research, we want our numbers to be as precise as possible. And to do that, we need better equipment. We need better technology or better instruments. Okay, so with reading significant figures, there are some rules. So to determine the number of significant figures, and I'll refer to them often as sig figs because significant figures is a mouthful and sig figs is easy to say. So the number of sig figs, right, we're going to look at a few things. First, we look at non-zero digits. So any number that's not a zero, like the 5, 8, 3, those are non-zero numbers. They are significant. We care about them. Leading zeros. A leading zero is if any zero that comes before your first non-zero. So our first non-zero here is the 5. Those zeros in front are leading zeros. They are not significant. Okay, so we are not going to be using these when we count significant figures. In between zeros are zeros, as it sounds like, it's in between non-zero numbers. So this zero here is between the 5 and the 8. That is going to be significant. They're always significant. And then trailing zeros, as it sounds, is trailing. It's after our last non-zero, right? So our last non-zero is a 3. The zeros after are they are significant if we have a decimal point. So here we do have a decimal point in the front, so it is significant. If we have a number like 30 without a decimal point, that is not significant. We only have one sig fig. If we have 30 point, now we have the decimal point, it is significant. We have two significant figures. So it doesn't matter where the decimal is, as long as there is a decimal in the number, the trailing zeros, the zeros after the last non-zero number, is significant. If we talk about scientific notation, right? So remember in scientific notation, we have something like 5.0 times 10 to the third, right? We're only going to look at the coefficient, the part before the multiplication, for significant digits. So in 5.0, there's two significant digits there. We have the 5, and then we have the trailing 0 with the decimal. Okay. And then we have some rules for math. For multiplying and dividing, you're going to use the number of significant figures as the original data with the lowest number. So for this example here, right, if we do say 2 times 5.0. That gives us 10.0, right? But our numbers here are 2 only has one significant figure. 5.0 has two significant figures. So our answer should have the same number as the least amount, which is 1. So to change 10.0 to one significant figure, we used to have a 10 with no decimal point, because remember, trailing zeros without decimal points are not significant. So only that 1 is going to be significant there. For adding and subtracting, we're looking at decimal places. same thing, but the least amount of decimal places. So if we have 2.15 minus 1.1, right? The answer there is 1.05. But if we look at decimal places, we have 2 there, 1 there. Our answer should only have 1 decimal place. So we should stop after the first decimal. We're going to look if the number after rounds it. So it's a 5. Remember, 5 or more, that is going to round up our number. So 1.05 becomes 1.1. So remember, with rounding, 5 or more rounds it up. 4 or less stays the same. Okay, so let's do some practice with this. I'm going to do half of these. I want you guys to do the other half on your own. So if you want to pause and practice these first, you can. But I'm going to give you the answers for all of these. Make sure you do it first for the ones I circled though, okay? So for the first one, 250.7, right? We have non-zero digits. Those are significant. We don't have any leading zeros. We don't have any trailing zeros, but we do have an in-between. That in-between is significant. So we have 4 total significant figures there. For 0.0007, we have those 2 non-zeros. Then we have a bunch of leading zeros. Remember, leading zeros are not significant. So we have 2 there. And then 4.7 times 10 to the negative 5. Remember, scientific notation, we only look at the coefficient. We don't look at the remainder. For 4.7, that's 2 non-zero integers. So we have 2 significant figures. Okay. For these other ones up here, you should get 2, 4, and 4. All right. So that's just counting significant figures. For doing math with them, so 35.45 times 23.46, that gives us 809.37, right? Note, I'm doing the math first before I look at significant digits. Okay, so looking at significant figures, my answer should have the same number of sig figs as the number with the least amount in my original question. So 34.5, that's 3 sig figs. 23.46 has 4 sig figs. So my answer should have 3. So I need to go to 3 sig figs, stop there. So 809, that 3 after the decimal does not round up my 9, so I'm good. So 809 is my answer there, with 3 sig figs. Okay, this addition down here, 21.78 plus 45.86, my answer there is 67.64. And remember, with addition or subtraction, I'm looking at decimal places. So here I have 2 decimal points, or 2 numbers after the decimal point, and here I have 2 after the decimal point. So my answer also has 2. So my answer is 67.64. It stays as that. Okay. And then for the last one, we'll do together 123 divided by 3. If we do that in our calculator, we get 41. Okay. However, remember, with multiplication division, we're looking at significant figures in our original numbers. 123, that's 3 significant figures. 3 is just 1. So how would we change 41 to be 1 significant figure? Because we have 2 here, right? We have the 4 and the 1. We need to kind of simplify the number. Remember, trailing zeros don't count if there's no decimal point. So that's going to change to 40. Okay. So if you need to cut back on significant figures, but you can't get rid of a decimal point, you need to change your last number to a 0 or to the closest 10, I would say, right? So if you have like 53, that'd become 50. If you have 57, that rounds up to 60. Okay, so be careful with that. Be careful with rounding and significant figures. Right? For your other ones, you should get, make sure you do this on your own first, but you get 9.29, 12.9 down here, and then 3 on the last one. Okay, so make sure you know significant figures. There will be some questions that test for significant figures without asking you specifically for it, right? You might have a math question that asks like the stoichiometry, right? It asks the stoichiometry question, how many moles do you have? And it wants the moles to the correct number of sig figs. And if you don't do it, if, for example, you write 41 instead of 40, it'll count it wrong, okay? It's not gonna happen often, but there are some times on the AP test when they'll do that. So I'll do that on my exams also. So be careful with significant figures. Okay, so moving on to electrons. We have different states for electrons. So remember, with electrons, you have the nucleus, then you have some energy levels, or those rings around it, okay? We start off on the ground state. The ground state is where the electron is originally at. It's its lowest potential energy. It's the lowest energy state it can be at, okay? When it gets excited, it's gaining energy. Energy is absorbed. So it jumps up a level. It can jump up more than one level. I'm just going to show it with one level here, though. Okay, so excited states jump up a level. For relaxation, it's going to go back down. It releases energy. So it's going back down to a lower energy state. And for excitation, relaxation, when it releases energy, that's when it releases electromagnetic radiation. We'll talk about that here in a minute, but that's light, right? So with excitation and relaxation, this image here on the right is important to understand. You need to know the Lyman series, Balmer series, and Paschen series. Essentially what this shows you is that the Lyman series is relaxation going to the first energy level, right? These numbers on the left are the energy levels. Balmer series goes to the second energy level, and Paschen goes to the third energy level from wherever it was at originally, okay? Why that's important is because you'll see as you go up energy levels, the space between them gets smaller, right? The smaller space, the less energy there is. So Lyman series releases more energy because it's a longer path than Balmer series, and Balmer releases more than Paschen, okay? You need to make sure you understand that concept with these, but there will not be any math regarding that. Okay, so with excited electrons, when they're gaining energy, remember these excited electrons go from the last paired electron to the next open position. Okay, so with these examples here, right, remember S2S2, that's 2 paired together, 2P2, that's 3 boxes, but you only have 2 electrons. So that last paired one is going to go to the next available position. That's how you get that 2P3. Same thing down here, 2S2, 2P4, right? The last paired electron is going to go to the next available position, which in this case is going to be a new box, the 3S. That's how you get a 3S1, okay? So it can double up in that new position, but not in the same box. So a 3P is not going to go to a 2P here is not going to go to another 2P. It's not going to go to one of these two spaces because that's the same energy level. It's going to go to a higher energy level, right? So if we look at this question here, which of the following is the electron configuration for an excited state of Na+? So remember, Na+, we have 1s2, 2s2, 2p6, 3s1 for Na, but the plus sign means we lost an electron. We lost that 3s1. So we don't have that anymore. Okay, so in an excited state, we draw this out. We have the 1s1, the 2s2, and then the 2p, we have the 3 orbitals, the 3 boxes. 6 electrons means they're all put together. The last paired electron, so our last 2p, is going to go into the new box. So it's going to go to our 3s. So we should have 2p5, 3s1 when it's excited, right? The beginning stays the same. The 1s2, 2s2 stay the same, but 2p becomes the 5, 3s becomes the 1. The one that shows that is going to be B. No, not B. D. Sorry. Okay? So you need to be careful with that because A shows that 2p5, but it does not show the 3s1. Okay. B has a 3s1, but it does not have the 2p5. So be careful with when you're reading the answers. Okay, so it's for excited electrons with electron configuration. The last paired electron moves to the next energy. So I am going to let you guys do this. So write the ground state electron configuration, right? I'll go ahead and do that. So for F minus, it is minus means it gained an electron. So it's 1s2, 2s2, 2p6. Mg2 plus, the 2 plus means it lost 2 electrons. So that actually has the same electron configuration. It's isoelectronic with F minus. Don't forget that vocabulary word. And then the excited state electron configuration, I want you to go ahead and pause and try to do that. Get the last unpaired electron, the last paired electron, move it up to the next energy state. So go and pause and do it, but I'll write the answers down. These are actually going to have the same answer because they are isoelectronic. So it'd be 1s2, 2s2, 2p5, 3s1. Okay, for the excited state. And then when it relaxes, it goes back to the original. All right. For electromagnetic spectrum, right, when we're talking about electrons, they have a duality, right? We're talking about with waves and with photons, so as light or as particles. Okay, so with this, we will have some math. So some important variables to know. We have c, lowercase c, is the speed of light. Okay, it's normally 3 times 10 to the 8. You can also see it as 3 times 10 to the 17, based on the units. 8 is in meters per second. The 17 is nanometers per second. Okay, and remember with variable or with units, if you see the s to the -1, that means it's the same thing as saying nanometers per second. So to the -1 means it's in the denominator for the units. Okay, so make sure you are able to distinguish between nanometers and meters, because in your questions, whenever you're asked, it can ask either way. It can ask you for the wavelength in meters or the wavelength in nanometers. All right. And on your reference sheet, it only gives it as 3 times 10 to the 8. So I would get accustomed to using that and then converting using the meters to nanometers conversion, because nanometers is listed on your reference sheet for AP. Okay, but c is speed of light. This V looking thing, it's called a nu. Nu is your frequency. The units for frequency are per second, so 1/second, or you can also have it in hertz, Hz, which is hertz. Okay. This Greek symbol, the third one, is a lambda. Lambda is your wavelength. That can be in meters, centimeters, nanometers, any of the meters units. If you see this A, it should actually be an A with like a circle on top. That's called angstrom. Angstrom is 10 to the -10 meters. The reason that's special, it has a little A, it's a very common because that's the typical size of bonds in compounds. Bonds or atom sizes, radii, okay? So any of the meter units, the length units, that's your wavelength. Again, make sure you know conversions. E is your energy, normally in joules, can be in joules per photon. Be careful with what the question asks. And then H is Planck's constant. It is a constant. It's always 6.63 times 10 to the -34 joules seconds. Okay, and that is on your reference sheet, so you don't have to memorize that. Okay, you don't have to memorize constants. All right, so the math what we're going to use for that is right here on the right. So you can convert between wavelength and frequency using C equals lambda nu. So speed of light is equal to the frequency times the wavelength. When we talk about energy, you have two equations. Energy is equal to Planck's constant times the frequency, and energy is equal to Planck's constant times the speed of light divided by the wavelength. Okay, you can, let me see. No, I'm not going to measure that. Okay, so you have these three equations. All of these equations are on, or sorry, not all of them. This third equation is not on your reference sheet. The way I got that is I rearranged this one on the top, right? So if I solve for nu there, nu is equal to C divided by lambda. That can get plugged in there, so E equals hc divided by lambda. That's equal to that third equation. That third equation is useful because you can go between energy and wavelength, but that is not on your reference sheet. So I would suggest knowing this substitution. It'll make some math easier. If you want to do it in 2 steps, you do this math first to find frequency, then this math second to do energy. You can do that also, whatever works best for you, right? But these 2 equations in red are on your reference sheet. Okay, so the math with this will go between wavelength, frequency, energy, and sometimes it's energy per photon, so you might need to do some dimensional analysis with Avogadro's number, so be careful with the wording of questions. Okay, so the electromagnetic spectrum looks something like this. What we're looking at is different types of radiation, different types of light, right? You've heard of these before: radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma. And we're looking at the wavelength and the frequency. Okay, so that's shown in this image here. Remember, wavelength is how long it is from crest to crest or trough to trough, the length of the wave. Frequency is how often it's happening, right? So on the left here, it's kind of slow. On the right, it's going pretty quickly. So with electromagnetic spectrum, the energy, so the energy of the wave is higher with a higher frequency and a lower wavelength. For lower energy, you want a lower frequency and a higher wavelength, okay? So the relationship between wavelength and frequency, if they are opposite, the word for that is an inverse relationship, right? If it's inverse, one is increasing while the other is decreasing. Between wavelength and energy is also the same. It's going to be inverse. And then frequency and energy, if one increases, the other one also increases. So this is a directly proportional relationship, or a directly proportional relationship. Okay, so make sure you understand the relationship between these variables, understand energy. Okay, if we look at this question here, right, if we have this diagram showing the photoelectric effect, which means that energy is coming in to a metal, and the metal surface releases electrons. The energy that's coming in is 3.3 times 10 to the negative 19 joules. What is the frequency? Okay, so remember we had the equation E equals H nu. So E is energy, H is Planck's constant, nu is the frequency. We can rearrange this to solve for frequency. So frequency is equal to E divided by H. We said our energy was 3.3 times 10 to the negative 19 joules. Our H, Planck's constant, is 6.63 times 10 to the negative 34 joules second, right? That comes from your reference sheet. And if you do that math, you get 4.977 times 10 to the 14. So 4.977 rounds up to 5, and we said times 10 to the 14, so it's C. Okay, so that's just, it looks complicated, right? It brings in something like the photoelectric effect to make the question seem a little more complicated, but it can be very simple. It's just need plugging into an equation. Okay, sorry with this, I didn't realize that would go down in slideshow mode. But for the electromagnetic spectrum, with these different regions of light with energy, they have different spectroscopic techniques. So these are techniques are used in research or they're used in everyday life, right? So radio waves is used in nuclear magnetic resonance, NMR. This measures the nuclear spin and is used to study molecular structure. It's used quite often in research. Microwaves is rotational spectroscopy. This talks about the bonding and intermolecular forces. Okay. This also makes molecules rotate. Okay, so with a microwave, a household microwave, what's happening is it uses microwaves and it rotates the water molecules in your food. That's what heats it up. Infrared is for infrared spectroscopy, for your transmitter, I think it was, infrared spectroscopy, and Raman spectroscopy. These have bonds vibrate. So bond vibration tells you molecular structure. So we have rotation, we have vibration, okay? With UV or visible light, this is UV-vis spectroscopy or atomic emission spectroscopy. This transitions the electrons. That's excitation or relaxation, right? And then X-rays and photoelectron spectroscopy, we'll talk about that here in a minute, tells you the electronic structure in an atom. Okay, so these are good to know. It's good to know the rotation and vibration of microwave and infrared. But you aren't tested a lot on spectroscopic techniques. Sometimes you are, like photoelectron spectroscopy we'll talk about here. We've talked about mass spectroscopy. That's another technique that's used, but it's not very often tested aside from these direct ones. Okay, so photoelectron spectroscopy, again, it's a mouthful, PES. PES is the process of bombarding an element with energy, with those X-rays, right? We said X-rays for PES, to remove the electrons and determine ionization energies. Remember, ionization energy is the amount of energy you need to remove an electron. So you're bombarding this atom with energy to remove the electrons and it sees how much energy it needs, right? But based on that, we can see what atoms we have. So photoelectron spectrum, PES, looks like this. On the x-axis, you have the binding energy, so that's the amount of energy that was needed. The y-axis is the number of electrons. Okay, so when it's closer to 0, remember, you're further away from the nucleus. It's less pull. The higher the energy, the closer to the nucleus, right? So when you're doing that with, say, electron configuration, right, if you have like 1s2, 2s2, 2p6, 3s2, the start is closer to the nucleus, the end is further. Okay, so you can actually assign electron configuration based on the PES. So the very first peak you see, the highest peak, I'd say actually, because sometimes this can be flipped, so be careful of your axes. The highest peak numerically is going to be your 1s. Okay, and since there's more after this, we know this 1s2, it's going to be full. So that means every 2 bars is going to be 1 electron. All right, so the next one after, so our second peak right here, this is going to be the next part of the electron configuration. This is our 2s. Okay, it's the same height. We have 4 bars, right? So that means we have 2s2. We have 2 electrons there. And then after that, we have 3 bars, right? So we have 3 electrons. This is going to be the next one. This is a 2p, and it goes to 3. So just from this graph, we can tell our electron configuration is 1s2, 2s2, 2p3, and that element with 2p3 is going to be nitrogen, right? So just from this spectrum, I can tell you electron configuration, I can tell you what element I have, I can tell you about the bonding energies, which one, I talk about compare atoms, which one needs more energy, which one needs less energy. There's a lot you can do with these PES, okay? So let's look at this question here. For this one, we have 3 PES, and they're not labeled, but we know we have aluminum, oxygen, and lithium. We have 3 spectra. We need to identify which graph goes with which element, and it says to explain our reasoning. Okay, so let's start with writing our electron configurations out for these. Aluminum, oxygen, lithium. Aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. Okay. Oxygen is 1s2, 2s2, 2p4. and then lithium is 1s2, 2s1. Okay, so if we look at our graphs, remember the side with the bigger number, so on all of these it's going to be the left side, is going to be closer to the nucleus. So our first peak is going to be our 1s for all of those. Okay, something you can note here is this first graph goes to 100. The second and third go to 1,000. So the first graph, this element is going to have a weaker pole than the other two graphs are. All right, but so for the first one we have 1s2, then 2s1. Right? So if you look at the number of peaks, 2 peaks means 2 electrons, or sorry, 2 bars means 2 electrons. This one's only 1 bar, so it's 1 electron. So we have 1s2, 2s1. For the second graph, right, it's going to be the same thing. That's 2 bars is 2 electrons, so 1s2. The second peak is going to also have 2 electrons because same height, so 2s2. The third bar, 2p, if each bar is 1 electron, we're at 1, 2, 3, 4, 2p4. The third graph, right, we start with 1s2. The second one is same height, 2s2. The third one's 1, 2, 3, 4, 5, 6, 2p6. Then we have 2 bars, that's 3s2. And then 1 bar is 3p1, because it only goes up 1 time. Okay, so we can match these based on electron configuration. So our rightmost graph is aluminum, center one is oxygen, the first one's lithium. Okay, and we're doing this just based on the electron configuration and reading the peaks on the graphs. All right, so going on to magnetism. We're still talking about electrons, but a different aspect of it. So magnetism comes from the spin of electrons. Okay, so when you're spinning electrons, they can either be diamagnetic or paramagnetic for the element. So diamagnetic is not magnetic. Paramagnetic is magnetic. And that depends on if the net spin is 0 or non-zero. So what this looks like, let's look over here. We have 2 electron configurations here. One of them is fully paired on the left side, right? There's no unpaired electrons. On the right, though, we do have 1 unpaired electron. If it's unpaired, it's not balanced. And if it's not balanced, it is not 0 for the net spin. On the left side, if it is balanced, that's not used to balanced, balanced, the net spin is going to be 0. Okay, so what this means is if it's diamagnetic, everything's paired together, net spin is 0. Paramagnetic, you have an unpaired electron, it is not going to have a net spin of 0. And the more unpaired electrons you have, so if you have, right, so this example, we only had 1 unpaired electron. If you have 2 unpaired electrons, or if you have 3 unpaired electrons, the more unpaired you have, the stronger the magnetism. Okay, you typically won't see questions about that, but it's just a point that I got asked about last year, so I thought I'd mention it here. Okay, and anytime we talk about metallic properties, right, because magnetic compounds are normally metallic, and time we talk about metallic properties, it is easy to lose those electrons, right? It has a Cl electrons, it gives it away quite easily. Okay, and then moving on to Coulomb's law. Coulomb's law, even though this is unit 1, this is a very important topic. Okay, this tells us a lot about the periodic trends. It tells us about strength, about bonding, about reactions, and it's quite often tested on AP tests, right? As not just a math, or I mean, it typically doesn't have math. I have not normally seen you have to do calculations with the equation, but you do have to use explanations with this. So what Coulomb's law does, it is this equation here on the right. It tells you that the force between two particles is directly proportional to, that's what you'll see in alpha symbol, directly proportional to the charges of the two particles. So Q is the charges, and inversely proportional to the distance, right? So the charges, if you increase the charge, it increases the force. If you increase the distance, it decreases the force. That's what that's telling you. Okay, so you'll either see it with the alpha or you'll see it with the equal sign like it shows on the right side. They both mean essentially the same thing. I think actually in your reference material it shows it with the alpha. So make sure you understand what alpha means. It just means it's proportional to. Okay, and this you can use when talking about two electrons or two different particles. We'll normally talk about it with the nucleus and electrons. Okay, so that's Coulomb's law. The second part of this, we'll talk about electron shielding. Electron shielding is kind of what it sounds like. The electrons are shielding each other. So you'll see here on this image on the right, you have two energy levels, right? You have two shells. Even though all the electrons are being pulled in by the nucleus, right? They're all being pulled in. Electrons do repel each other because they're negative. That's what these blue arrows on this image are. So the electron shielding is the inner electrons push out on the outer electrons. It's repelling them. It's shielding them from the pull of the nucleus. Okay, so the more electrons you have, so if we have two nuclei, the first one has two energy levels, right? That's going to have some push because you have two electrons there. Those are both going to push off. If you have another element that's similar, but now instead of only having two energy levels, it has more energy levels. I'm not going to draw all the electrons, but this electron, say out here, it's going to get pushed by all of these electrons, all the inner ones. Okay, so even though the nucleus is bigger, there's more protons in the center there, the push from the outer electron or the inner electrons still has an effect. Okay, so that's electron shielding. It's the inner electrons, the ones on the inside, pushing the electrons on the outermost ring. Okay. And then the third part of Coulomb's law is effective nuclear charge. This one you may have to do math with on test, so make sure you know this equation. This equation is not on your reference sheet. So this is one of the ones you actually need to know. You need to memorize this. But it's the total pull on electron fields from the nucleus. Okay, so effective nuclear charge, the equation is right here. It's ZeFF is the effective nuclear charge. Z is normally charge. So the EFF is effective. Effective nuclear charge equal to the nuclear charge. So this is the atomic number, right? This is the number of protons you have, minus your inner electrons. Let me write it a little better. Your inner electrons. Okay, so in this image here, right, we have 15 protons. So our atomic number is 15. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inner electrons. So our effective nuclear charge is going to be 5 here. Okay, it's always going to be a positive number. If we're talking about, in this case, the nucleus 2 electron, it's going to be a positive number. Okay, so that tells us how strong it's pulling on the electrons. Okay, so the trend for shielding on the periodic table, right? As you go down, you're getting more energy levels. Okay. As you go across, you're staying on the same energy level, but you're increasing the number of protons. Okay. So if you're increasing the number of protons, if you go across the energy, or sorry, across the period, you're increasing your Z effective, your effective nuclear charge. And then as you go down the group, you're increasing the number of NR electrons, you're going to decrease your effective nuclear charge. Okay. And that's also based on shielding, because as you go down a group, your shielding goes up. You have more NR electrons. Okay, so that's how it's all interrelated. You can also relate this to periodic trends. Okay, so let's talk about the periodic trends really quick. So if you, for ionization energy, right, ionization energy is the pull to pull off an electron, right? So if ionization energy trend was like that, you're going to the top right of the periodic table. Across the period and up a group increases ionization energy. The reason for that is you're increasing, right? If you go across the period, you're increasing the number of protons, so that increases your effective nuclear charge. As you go up period, you're decreasing your inner electrons, so that decreases shielding. Okay. The other trends are going to have similar reasons. Same thing for electronegativity. And then atomic radius is going to be the opposite. So if you go the other way, right, it's going down a group and to the left of a period. So atomic radius gets bigger because there's less protons relative to the period. So it's less charge, less nuclear charge. And there's more shielding. Okay. So let's look at this question down here. For element X represented, which of the following is the most likely explanation for the large difference between the second and third ionization energies? So looking at element X, right, the second to third ionization energies, it jumps quite a bit, right? So remember, we've talked about this with unit 0. So let's read these questions, or let's read the answers, sorry. A says the effective nuclear charge decreases with successive ionizations. Okay. Remember, with ionization energy, you're moving the electron. So that does not affect the nuclear charge. We're not removing protons, because nuclear, that's your protons, it's your nucleus, protons and neutrons. Okay. For B, the shielding of outer electrons increases with successive ionizations. Okay. So remember, if we're moving electrons, we're removing from the outer layer. So if we're removing from the outer layer, so if we get rid of one, it's not changing the inner electrons. So if we're not changing the inner electrons, the shielding is not changing. So it's not right. With C, the electrons are moved into third ionization on average is much closer to the nucleus than the first two electrons. Well, that would make sense, because the closer it is, the less shielding, right? If you have an electron on these two levels, the one on the inner level has less shielding, so it's got a stronger pull to the nucleus, so it would take more energy. That does make sense. And then D, the ionic radius increases with successive ionizations. Well, that doesn't tell us anything about ionization energy increasing, right? It's not related to the question, whether it's true or not. So we know the answer here is C. Okay, so remember, when you're doing these questions, test-taking strategies, go one by one, eliminate the ones you know are wrong. Okay. All right, so with this question here, this is something similar to what you might see on an AP test. So using the principles of atomic structure and or chemical bonding, explain each of the following. So the atomic radius of lithium is larger than beryllium, and the second ionization energy of potassium is greater than the second ionization energy of calcium. When you're doing questions like these, specifically when it says atomic structure, you want to mention something about the effective nuclear charge, so talking about the protons, and you want to mention shielding, so the electron aspect of it. and relate them to Coulomb's law. So when doing these questions, you want to have all these pieces in this. Sometimes on AP questions, if you do one part but you forget to do another, they won't give you the points. They want to see all the parts in here. Okay, so we'll do A together. For A, right, if we're looking at lithium and beryllium. So for lithium and beryllium, they are both on the second period, right? So on the periodic table, you have hydrogen, lithium, beryllium, right? So they're both on the same period. So they have the same valence shell, the same outer shell. So that means that they have the same number of inner electrons, right? And remember, with writing, you can write the E minus, even on the AP test, that's fine. But the same valence shell means that there's the same number of inner electrons. However, we know that lithium has, how many? It has 3 protons. And we know that beryllium has 4 protons based on the atomic numbers, right? The number it falls on the periodic table. So that tells us that the Z effective, the nuclear charge of beryllium, is going to be greater than the effective nuclear charge of lithium from these two facts. Same inner electrons and a different number of protons. Okay. So we know that if the effective nuclear charge is greater in beryllium, beryllium is greater than the effective nuclear charge of lithium, then beryllium has a greater pull on its outer electrons, so it would have a smaller atomic radius. Okay, and that would be an acceptable answer, right? So see how we talked about the electrons, talked about the protons. We are related to Coulomb's law with nuclear charge. Okay, and then from there, we put it into a concise sentence. If you have all of this on your question, that would be given the point. So I want you to try to do the same thing with part B. Okay, so try to do the same thing. If you have questions about that, let me know. But make sure you have all the pieces. Talk about the electrons, talk about the protons, talk about Coulomb's law, put it all together to make sure you answer the question. Okay, and there would be the answer there. So make sure you read that. Make sure you try on your own first, then read that, see how your answer compares. All right, the last part of these notes is quantum numbers. Quantum numbers, if you're on on-ramps, you've already talked about these before. If you're in advanced, you didn't really talk about these, but that's okay. So quantum numbers describe electrons in terms of their location and their shape. Okay, there's some important people when it comes to talking about quantum numbers, right? Bohr talked about the quantized energy level. Planck talked about the particle nature of the wave. De Broglie talked about the wave nature of the particle, right? We've talked about particles and waves. And then Heisenberg and Born, you probably heard about this, Heisenberg's uncertainty principle. It says that the position and the momentum of an electron can't both be calculated to exactitude, right? You can calculate one, but if you do one with more precision, the other one is less precise or less accurate. Okay. And then Schrödinger also talked about the possible probability of position. And with Schrödinger, he has what we call wave functions. So it's this trident-looking thing, I believe it's psi, the Greek letter psi. That is a wave function. We will not be doing any math with wave functions. That is an upper-level chemistry course that if you major in chemistry or biochemistry, you will take it. If you do not, you will not be taking it, most likely. Okay. But with wave functions, what they mean is the square of the wave function tells you the region in space where there's a 90% chance of finding an electron, So it's the chance of finding the electron. And then the wave functions are described by the 4 quantum numbers. Okay, so the 4 quantum numbers are N, L, M sub L, and M sub S. Okay, those are the 4 that you will need to know. This information up here is good to know, but you should not be tested on that. You would be tested on the N, L, M sub L, and M sub S. Okay, so this page gives you a little breakdown on each of them. It shows all of them together, but we're going to go one by one. So N is the principal quantum number. This tells you how many energy levels there are, right? So image here, the first energy level, the first ring is 1, second one is 2, third ring is 3, fourth ring is 4. It's pretty simple. The number of energy levels is N. There is an equation that goes with this. This equation, I do not believe AP will test you on it at all. So you don't need to worry about memorizing this equation. Okay, but what this equation does is it relates the energy of the particle to a direct proportional to the nuclear charge and an inversely proportional relationship to the quantum number, or the number of energy levels. So the more energy levels there are, the further away the electrons get from the nucleus, the smaller the energy. Okay. And a little note, you also probably shouldn't be tested on this, but each energy level can hold up to 2 n squared electrons. So what that means is your first energy levels holds 2 times 1 squared electrons, which is 2. Your second energy levels hold 2 times 2 squared, that's 4 times 2 is 8 electrons. Third energy level is 2 times 3 squared, so 9 times 2 is 18 electrons. Fourth is 2 times 4 squared, so 16 times 2 is 32 electrons, and so on and so forth. So if you need to know how many electrons you need to put on an energy level when doing something like a Bohr model and you forget, you can quickly make sure with that equation. But again, that equation is not on your formula sheet. Okay, your L quantum number is the angular momentum quantum number, and this describes the subshells. Okay, so in class, I do have some models for this. You've probably already seen it at the front of class, but we have some subshell shapes that look like these on the image on the bottom. So the S is just a sphere, and then the P, we have like these dumbbell looking shapes, right, or figure eights. And we have 3 different ones, one on the x-axis, one on the y-axis, and one on the z-axis. That's why for P, we have 3 boxes, because it's PX, PY, and PZ. That's what that means. For D, there's 5 iterations of it. That's why for the D subshell, we put 5 boxes. That's D, I don't actually know all of these, but that's those 5D shapes that can happen. Okay, and what these shapes are is it describes the regions where electrons can be found. You can also see this graphically, right? So probability curves, the node. So the node is where it touches the x-axis. That's where the probability approaches 0. So that means the electrons are not there. And then the greater area under the curve, the greater the probability the electron will be there. So you can see with S, that red line, the electron can be within like 300 picometers, PM is picometers, from the nucleus. With the blue, you have a small chance of it being within 100 picometers, and then a bigger chance of being about 300 picometers but it can be between 100 and 700 there too, right? So that's for the 2s, because you have 2 electrons there. So let me erase those. And then for the green, 3s, right, you have 3 energy levels. You have a small chance at the beginning, under 100, slightly larger, but still small chance between 100 and like 350-ish, and then a larger chance at about 700 picometers from the nucleus to find an electron. So all these shapes tell you is the probability of finding an electron. Okay, that's what L is. M sub L is the magnetic quantum number. And remember, with magnetic, we talked about spin. So this tells us the orientation, okay? So it's either +1, -1, or it goes based on how many you have. So for S, you only have one box, so it's 0. The center box is always going to be your 0. From there to the right, you increase by 1 each time. To the left, you decrease by 1 each time. And it describes the orientation of the orbital, okay? So for example, remember with P, we said there was 3 iterations. That's why there's 3 boxes. One is the -1, one is a +1, one is a 0. And then with M sub S, again, magnetic, that's the M. This one's for the spin. So the up arrow, down arrow. If it's an up arrow, it's +1/2. Down arrow is -1/2. Okay, that's why we have the up and down for the arrows. It just indicates the spin. Okay. And this last slide is a summary of all those quantum numbers. These aren't tested too heavily on AP tests, but I would understand what they mean. You will have some practice questions about this in your practice packet. All right, so as always, if you have any questions, make sure to ask them during tutoring or come into me or come and ask questions during class. I'll be happy to help you. Okay, make sure you understand Coulomb's law. All right, a lot of what we talk about in this unit is important, but I would say Coulomb's law is the most important thing we talked about in this unit. Some of the important things are small details, though, that can sneak up on you, like significant figures. Don't forget your significant figures. All right, so make sure to practice those. If you have questions, let me know, and I will see you in class. Have a good day.